Okay, this is a worked example for hypothesis testing with a normal distribution, including, of course, the sampling distribution is what we're using. And this one's to do with what's called Dipak's forest. Let's have a look. A certain forest contains only trees of a particular species. Dipak wished to take a random sample of 5 trees from the forest. He numbers these from 1 to 784. Then, using his calculator, he generated the random digits 14781049. Using these digits, Dipak formed 5 3-digit numbers. He took the first, second, and third digits, followed by the second, third, and fourth digits, and so on. Right, okay. I'd probably see that it's better in the actual numbers that he's actually produced. Can you see these kind of drawn from this 147? So he's saying 147, then he's saying 478, then he's saying 781, 810 he has discarded. And that's the first question why he's missed that out. And then 104 and 049. So those are the 5 he's produced. And the first question is, explain why Dipak omitted the number 810 from his list. Well, of course, the trees are numbered up to 784, so a number of 810 is not of any use. And explain why Dipak's sample is not random. Well, this is quite a good question, actually. Because you might sort of say, well, any number is as likely to come up as any other number. But these numbers, in fact, are not actually independent, are they? You know, the second one is constrained by the first one, and the third by the second, and so on. So therefore, they're not actually random numbers. If you use the scheme like this, you know, how different would the outcome be to actually generating truly random numbers is a good question. You might want to ponder on that a while. But anyway, that's simply the answer to that part of the problem. The mean height of trees of this species is known to be 4.2 meters. Dipak wishes to test whether the mean height of trees in the forest is less than 4.2. He now uses a correct method to choose a random sample of 50 trees and finds that their mean height is 4.0. It is given that the standard deviation of trees in the forest is 0.8. Carry out the test at the 2% significance level. Okay, so now what we've got, going back to our sampling distribution, what we've actually got is he's actually taken the mean height of 50 trees. So the random variable, which is the mean height, you know, divided by 50 if you like, some of your sample divided by 50. So that is normally distributed with a mean of 4.2 and a variance of 0.8 squared. That's of each individual tree has got a standard deviation of 0.8 from the mean. So the variance is 0.8 squared. But the variance of our sampling distribution, that's of these x bars, is going to be 0.8 squared divided by 50. Now, if you're unsure about that, go back to the lesson video to understand why that is the case. So I'm just kind of recapping there. So that's going to give us a standard deviation for the sampling distribution of this 0.1131. Now, our null hypothesis is going to be 4.2 because he says it's known to be 4.2, but he's trying to establish whether or not there is that it's different for this particular forest. So so that will be our null hypothesis, and we're going to do a one-tailed test. Why one-tailed? Well, because he wishes to test whether the mean height of trees in the forest is less than 4.2 meters. So that would give us this situation here, so where that alternative hypothesis is less than 4.2. So that would lead us to a one-tailed test. Okay, so our actual sample is actually has got a mean of 4.0. That's this sampling distribution test statistic here is less than 4.0, and that, well, given this distribution here, and therefore we can plug this into our calculator and look up the probability that random variable is going to be less than or equal to 4, so we have to consider the whole tail of the distribution. So how likely is it that we've got a result as extreme as 4.0 is the question that we're asking ourselves, and that's got a probability of 0.0385. Now that is greater than our significance level of 2%, as prescribed by the question. So really we're in the area where we're sort of saying, well, yeah, it's not terribly likely, but it's still possible through random variation. It's not got so extreme that it's going to lead us to make a different assumption about the mean height. So so the conclusion is that we accept H0. Basically, there is insufficient evidence against the mean being 4.2 meters. Okay, so that is it really. So it's just another example of hypothesis testing with the sampling distribution, a little bit of kind of randomness thrown in there as well. I hope it's been useful. Thanks for watching.